the last concept we deal today is the capitalized cost, CC. So let's make a definition. What is that about? So capitalized cost is referred to the present values. That's why we apply in today's lesson net present value. So it refers to present value for what? Of a project that is assumed to last forever. Of a project that is assumed to last forever. So keyword is last forever. And what do we mean in engineering? A project lasts forever. A project, like if it can last 100 years or more, we can technically assume that it lasts forever. And with that, what project it be that we normally consider that lasts forever in engineering? So let's give some example. It's like a dams. When we build dams, we don't want to last only 10, 13 years, right? So it have to be last more, so it 100 years or more, like Hoover Dam, etc. Or irrigation system. Or even railroad. So all of that, it assumed to last forever. And of course, not only this concept apply in engineering projects, you can apply for other type of project that I can see here. You can see the permanent university or charitable organization endowment. You have a name in a fund or an endowment, a scholarship that lasts forever to ensure the name still there. And that we also use the concept of capitalized cost. So that want to the name of certain philanthropists that endow the money to the university, for example. You want that to last forever so that their name's still there, so they are happy to keep donation. So with that, we have another example. It can be permanent university or charitable endowment. Permanent university or organizations endowment. So that is the capitalized costs. So how can we do this? Let me draw a simple cash flow of the capitalized cost so that we can make use of this here. So if we have a continue, if we assume we have a project like a dam or a railroad, then we have a cash flow last forever, so it's years, and from year 0 to 1, 2, 3, etc. 4, 5, keep continue until last forever. Let's see that to infinity and beyond. So infinity. So at the beginning, to build a dam, we need to put a initial cost. Let me call that a P1. And of course, that's not enough. We have to maintain every years. You have a cost. Assume it's same amount over the years as long as you continue with that project. So keep continue until infinity when we demolish that dam or railroad or irrigation system, anything that you consider infinity, like I say, 100 years or so. So with that, the initial cost, let's copy one, and the same operating cost annually, call it A. The question is, how can I find out the capitalized cost? And they, by definition, that is present value of a project, present value. So basically that is NPV of this project. So with that, we want to find out here, capitalized cost of this one is the present value of this project, and assume to last forever. So in that one, I can have it P1, the cost. So it, and this is cost. So you don't have to put the negative because that is cost when you say cost already. So with that P1, and then we plus the annual cost, that is A, and we have to time the factor. So let me put that in plug here, P1 plus A time the factor, and in this case you have P over A, because print that to present value, because that is what is the capitalized cost defined. Let's see, I%, whatever I% we have to evaluate for how many years? Infinity years. Infinity. And the question becomes complicated. Let's go to the table. Here, for any percent, let's see 1.5%. And you have it, the project any 100 years is the maximum in the reference. But we have the n is infinity. So how can I do with that? That is the challenge. Make sense? And then with that challenge, how can we do? So let me consider the equivalent value of these components. Let me call that P2, because that is the equivalent present value of the annual cost A spending every year for infinity years, with the interest rate I% for infinity years. So let's find P2. P2 is equal to A, and that factor P over A, I% infinity. Let's go to that. We don't have infinity in the table. Then you have to use the equation. P over A I% infinity. That is the equation we need to use, because that P over A there. Okay, so with that, P over A 1 plus I power n minus 1 over I 1 plus I power n. So with that, we can have that equal to 1 plus I power n minus 1 over I 1 plus I power n. But our n is infinity. And when you say infinity, then in your calculus, you have to take the limit. Remember that. So with that, we can take the limit of n go to infinity of that factor. That factor equal to 1 plus I power n minus 1 over I 1 plus I power n. And if I divide the numerator and denominator with 1 plus I power n, then you have the equation become 1 minus 1 over 1 plus I power n. And then the denominator, if divided by 1 plus I power n, it become I. And with that one, as you can see, when you take a limit, then 1 plus I power n become infinity. 1 over infinity equal to 0. So the numerator is 1 minus 0 equal to 1. And I, it not depends on n, so that limit become 1 over I. So believe it or not, with this one, we have P2 equal to A over I. What does that mean? If you spend an amount or you receive an amount, same amount for infinity years, the equivalent amount now is equal to that A divided by the interest. So from that, we can see that the capitalized cost now become CC equal to NPV equal to P1, whatever initial cost you had, plus P2, in this case, it equal to A over I. And you can see that. So that is basically that is the capitalized cost. So what it is here, you can see that from the reference. If you go to that reference, you can see the second page of the here. They define the capitalized costs, and that is M2 reference definition. And if you spend an amount, the same amount over the years, the equivalent capitalized cost equal to A over I for that component. So with that, you can see that is the capitalized cost. Now, to solve that problem with the capitalized cost, in the last slide of today's class, we have this step to calculate the capitalized cost of the infinity sequence of cash flow. So that is infinity. First, you draw the cash flow diagram showing all the non-recurring costs and income, and at least 2 cycles of all recurring costs and receipts. So at least 2 cycles. Then find the present value of all non-recurring amount. Then find the equivalent uniform annual value through one life cycle of all recurring amount, but not every year. Then add this to all other uniform amount occurring from years 1 through infinity. And then we divide that amount with the interest rate, basically that realized with the capitalized cost. And then add all step 2 to step 4, then we will get the capitalized cost. So that is the step. Look abstract, but let's go to the next video. You will see apply that in problem 3, which is in here.